Today we will continue the series solutions near ordinary points. It's chapter 5.3. We have seen what do we do when we are given an equation like that. Capital Q, sorry. If PQR are polynomials, and if P of x naught is non-zero, we can use the power series solution, right? Y equals summation of an x minus x naught to the nth power, and go from 0 to infinity. Then plug in and do the shifted index if needed, and we get the recurrence relation between these coefficients. Then we'll get the two independent power series solutions. Okay, today we will just see more examples of that. Let's see the first example. It's called Chebyshev. It's named after Chebyshev, a Russian mathematician. And the equation is like that. 1 minus x squared y double prime minus x y prime plus alpha squared y equals 0. And once again, we have a parameter called alpha. And we will fix this alpha to be some special value in the end, as you can expect to get some finite series, which is a polynomial. Let's see. And as usual, we will just choose x naught to be 0. And this time, the first coefficient is not a constant anymore. However, it's still 0 when x is 0, right? So it is still ordinary. Because P of x naught equals 1, and that's non-zero. Okay, so we can still use the old method. And that's, let's say y equals an x to the n equals 0 to infinity. Right? But there is a little problem here. If you do the double prime, then you multiply that, you'll find out something wrong, because double prime will give you x to the n minus 2, right? Then time that, you get this. Well, they don't match by itself. How can we combine them, right? So the idea is to break them into two different parts. Let's say I erase this. So we don't do that. Instead, we will do this. Y double prime minus x squared y double prime. So I will write them separately. Y double prime, as we did earlier, we need a shift because otherwise you will have n plus 1 x to the n, you have a wrong power. However, for the x squared times the y double prime, we will get something different. This term is what we get directly, right? And if you times x squared, see what happens? And then they're gone. So you don't need a shift for that term. So that's why we break them into two parts, Term 1, shift. Term 2, no shift. And so we get everything matched now, right? We'll work on next term. X times the y prime. And if you remember, we don't need a shift for that either, because then you have n x to the n minus 1, right? But x will give you plus 1. So cancel it again. Right, so everything is matching now, right? let's go back to where we had. You have a term 1, term 2, term 3. Or you can say term 1, 2, 3, 4. Right? So minus, minus, plus. So let me write down y double prime minus x squared y double prime plus, no, not plus, minus xy prime plus alpha square y. Alright, let's see what we have. N equals 0 to infinity. And actually it's from 0 to infinity for every term. See? 0, 0, 0, 0, and of course originally also 0. So you have an plus 2, n plus 2, n plus 1, and minus x squared times y double prime. You just get n minus 1. n minus 1. Then you minus this term here, right? an times n. Then you plus this term here, which is an alpha squared. And of course, everything has x with n. Right? And then this equals 0. They tell us that this whole thing must be 0 for every n. And you notice that it has term 1, 2, 3, all about an, right? And only the first term is about an plus 1, n plus 2. So we can say an plus 2 times n plus 2, n plus 1 equals an, and move everything to the other side. So this minus becomes plus, plus, and minus. So you get n minus 1 plus n, minus alpha squared. Right, and what is that? That can be simplified. N squared minus n plus n. So that's what we have. Alright, and let's write down the fraction form. N plus 1, n plus 2. And n equals everything non-negative. That's almost done. So once again, because this 2 there, we will see, as usual, A0 will determine A2, A4, and A1 will determine A3, A5, right? And then you get 2 series solutions. But we are more interested in the special case. That is, one of the solutions either y1 or y2 will be a truncated series. That is, from some point on, this an will become 0. And that is possible only if this vanishes, right? When will that vanish? Well, n is an integer, so alpha must be same as that n. So it means alpha is an integer, right? Well, I cannot say alpha equals n because n is an index. So let me just say alpha is an integer. So let's say if alpha equals 0, then what happens? Then when n equals 0, this equals 0, right? And that means a2 equals 0. So y1, let me write down what is y1. Okay. Let me write down in general what is y1. Okay. Let me write down what is y1 first. So y1 equals 1 plus You plug in n equals 0, so you get negative alpha square, and 2, you get x squared. Then, remember what we do? We will write down the product next time, right? So let me just copy this. Then, because the relationship between and a0 and a2, then a2 and a4, so have a next one. Then plug in n equals 2, you get 2 squared, which is 4 minus alpha squared, and this is 3 times 4, which is 12, right? Like that. Okay, from now on, you should recognize this pattern, right? X plus something times x cubed, and something times x to the 5th, etc. And what is this? You plug in n equals 1. So, yeah, n equals 1. 1 minus alpha squared over 2 times 3, which is 6. And this time you are 6, 1 minus alpha squared. And then what do you have? This is 9 minus alpha squared. And this is 2 times 3, this is 4 times 5. So it's, 20. Like that. Okay? So, this is infinite. But if alpha equals 0, or 2, or 4, y1 is a polynomial. Right? Because when alpha equals 0, it's just 1. When alpha equals 2, then it's 1 minus 2x squared. It's also 1 minus 2x squared, like the Hermite polynomial. But then it will be different. Okay? And when alpha equals 1 or 3 or 5, and y2 is a polynomial. Right? Because you can see alpha equals 1, then this is gone, then this is gone. When alpha equals 3, that is gone, etc. Right? So the polynomial solution is called the Chebyshev polynomial. And if it's infinite, then just Chebyshev functions. Okay. All right. So that's the Chebyshev part. To get more practice, we will have one more example. Let's see. The next one is still named after a person. Legendre. And once again, if we get a polynomial, it's called Legendre polynomial, otherwise Legendre function. And this time it's a French mathematician. So we have Russian, French, English, all over the world. All over the world. So where is this equation? This equation looks almost the same as the Chebyshev one. So if you compare this with the Chebyshev, you will see the first term is the same. And this is the same, but this 2 is different. Last time we don't have a 2 there. But this little change will make a very big consequence. It turned out that we don't have alpha squared anymore. We have alpha times alpha plus 1. And in the end, alpha will be chosen to be an integer to get a polynomial solution. All right, so let's do it. It's very similar, actually. So you write down this as a, y double prime minus x squared y double prime. And so you can do the shift. The only difference is that you have an extra 2 there, right? And of course, this is also changed a little bit. So just let me copy paste. Okay. So let y be the ANXN. All right. Then let me just write down this term by term. Yeah, kind of bored by doing this again. So this, then x squared y double prime. But you still need to do it by a few times by yourself because you don't need to. You need to do practice by yourself. Okay. What is that? Then, okay, next term is xy prime, and you don't need to shift because the cancellation. Yeah, so no shift. And the next term is just y itself. So let's sum them up. Okay, let me just write down the equation. Okay, the first term is an plus 2, n plus 2, n plus 1. Then the minus, this term, n plus minus 1. Like that. Then minus 2 of this term. Minus 2n an. Then last term would be plus alpha plus 1 an. Alright, x and n. So very similar. So we get this whole thing must be 0. So an plus 2, n plus 2, n plus 1 equals an. Yeah, move everything to the right hand side. So you get n minus 1 plus 2n. See this 2 here? That's a new thing, right? Then, yeah, minus that. And that equals 0. No, not equals 0, sorry. We already have the equal sign. And then it can be simplified. N squared minus 2n plus, and minus n plus 2n. Aha, see that extra term? Then this will match this. Right? When alpha equals n, this will be same as that. So that explains why we have this alpha plus 1 here, right? Okay, so we are almost done. So an plus 2 equals an times n plus 1 minus alpha plus 1 over n plus 1 n plus 2. Alright, and that is true for every n. So let me just say what we have said 5 times. Like that, right? So let me just write down what is y1. y1 is always 1 plus something x squared plus something x to the 4th, right? Okay, what is that something? Oops. Plugging n equals 0 here, right? And then you get 0 minus that. So you have this over, and plugging in 0, you get 2, right? You get something very similar over 2, and n equals 2 there, right? You get 6 minus alpha plus 1 over 3 and 4, so it's 12, right? Okay, it's very similar. Then x2 equals x, sorry for that, and then cube, and x to the 5th. Alright, that's something you should know it very well now, right? So denominator is just that n equals 1. So it's 2 and 3, so that's 6. And the numerator is n equals 1, so 1 times 2 is 2. So 2 minus that. And this is similarly 2 minus alpha times alpha plus 1. And you can tell what's the next one. This is 2 times 3, so that's 4 times 5, which is 20. And the numerator would be, let's see what it is, n times n plus 1, so it's 12 because n equals 2, right? So you have minus alpha, n equals 3, right? Okay, so when will this be truncated? Well, when you have some kind of cancellation. Say, for example, when will this be true? When alpha equals 2, right? And when will this be true? Or when will this be 0? Alpha equals 1, and alpha equals 0, and alpha equals 3. So, when alpha equals 0, 2, 4, etc., what will happen? This y1 is a polynomial, right? And when alpha equals 1, 3, 5, y2 is a polynomial, right? So that's what happens. And by the way, these polynomials are called Legendre polynomials. Okay. And just for curiosity, let's write down what is what are the Legendre polynomials. And actually, it turned out that when alpha equals 0, you just get y1 equals 1, which is a 0th order polynomial. When alpha equals 2, you have x squared term, but no x to the 4th. So it's a second order polynomial. So it turned out that the number, the alpha, just give you the order of this polynomial. So for example, when alpha equals 3, you get a third order polynomial. Alpha equals 5, you get a fifth order polynomial. So, and let's write down the first few terms. Alpha equals 0, y1 equals, so you see there's nothing but the first term, so it's just 1, right? And then alpha equals 2, then you see here this is 2 cancel 2, so this is a negative 3, right? So y1 equals 1 minus 3x squared. All right, and then alpha equals 4. That's more complicated. Then you have 4 times 5, so it's 20. 1 minus 10. 1 minus 10x squared. Then alpha equals 4. Alpha equals 4. Then this is 4 times 5, which is 20. It's complicated. 6 minus 20 is negative 14. Negative 14 over 12 is negative 7 over 6. Negative 7 over 6. Then you plus 70 over 6 x to the 4th. Anyway, that's what you have. Right? So that's the Legendre polynomials. And similarly, you can write down what is alpha equals 1, 3, 5, etc. So you get this Legendre polynomials. Alright, so I think that's it for 5.3. And that's all the technique we need to learn for the ordinary points. And next class we will learn the singular points, and we have to modify the power series solution a little bit to solve that kind of cases. Okay, bye.